Okay. Thank you for your kind introduction. Ladies and gentlemen, good afternoon. Today I'm going to present to you the chiroptical spectroscopy, its principles, some applications and some examples from our laboratory. Chiroptical spectroscopy is limited to the analysis of chiral systems. So first of all, I'm going to introduce the concept of chirality. So what is chirality? The easy definition is the mirror image of a chiral object is not superimposable on its parent object. Sounds difficult, but it's pretty easy. The simple example are your hands. Your hands are mirror image to each other, and they are not superimposable to each other. You can try it, even if you cut them off, you never can superimpose one to each other. So, chirality is a very common natural phenomenon, and here you can see some examples in chemistry. Here you can see the simplest chiral molecule. It's carbon with 4 different substituents. And the more complicated example, helix, left-handed and right-handed. Again, they are mirror images, but you cannot superimpose them one to each other. Chiroptical spectroscopy is characterized by the use of linearly, or more importantly, circularly polarized light. And the principle of the chiroptical spectroscopy is the different interaction of chiral molecules with left and right circularly polarized light, which is schematically shown here. This delta A is the quantity we measure. The 3 most important methods from the chiroptical spectroscopy family are the electronic circuit dichroism, which uses radiation from UV or visible region of the spectrum. Vibrational circuit dichroism uses infrared radiation, and Raman optical activity is the variation of the conventional Raman spectroscopy. Maybe you're asking, chiroptical spectroscopy, what's so special about it? What is it for? What's the advantage? So it's shown here. The advantage is the sensitivity to the 3-dimensional structure of chiral compounds. If you compare it to conventional spectroscopy, for example infrared, the measured quantity is proportional to the square of electronic dipole moment. On the other hand, chiroptical spectroscopy, here the measured quantity is proportional to electrical and magnetic transition dipole moments, to the imaginary parts of their product. So, it depends on 2 quantities, not only one, and also on their mutual orientation. That's why. Here are some traditional examples of applications of chiroptical spectroscopy. We can determine enantiomeric purity or absolute configuration, and what I'm going to show you in a minute, we can perform conformational analysis of organic molecules, and we can analyze also biomolecules, which are usually chiral. So here's the first example. We investigated the 3-dimensional structure of heroin in a solution. I think I don't have to introduce heroin. It's a very well-known, widespread drug. You can see its structure here. And what we do, we run quantum chemical calculations, specifically calculation based on density functional theory. We obtain stable conformations. Then we optimize their geometries. And based on the calculated energies, we can estimate their relative abundances. So we could say we are done here, but this is only theoretical model, and we want to get some experimental proof that the theoretical model is correct. And that's where chiroptical spectroscopy comes in. We calculate the spectra for individual conformers, we calculate their weight average, and we compare it to the experiment. Here we got a very nice match between the theoretical and experimental spectra. Thus, it confirms that our theoretical model is right, and we know the 3-dimensional structure of heroin in a solution with a resolution close to the atomic resolution. Please note the difference between the conventional IR spectra of individual conformers and BCD spectra. You can see that the conventional spectra really don't differ much. On the other hand, BCD spectra are very different, mainly in this region. So that's the sensitivity of chiroptical methods to the changes in three-dimensional structure. The second example, our group tests new possibilities in diagnosis of pancreatic cancer, which is one of the 5 most aggressive tumors. Here is the example of usage of R-way Raman optical activity. You can see some marked differences, and the statistics is pretty good, almost 90% correct, which is very nice because analysis of the plasma is not so invasive as other methods. Thank you for your attention, and if you're interested in this, or if you want to get more, don't hesitate to contact us, and have a nice Valentine's Day. Thank you.
Thank you. Time for questions. Yeah?
How soon can you diagnose a tumor with that method?
One measurement takes approximately 24 hours. So you need to take plasma, measure, and yeah. It's like the beginning only, so.
Of the research?
Yes.
Okay, because my question was more like how soon in terms of the cancer progress in you?
That's actually the reason why we are doing it. That's a great question, because the commonly used methods struggle in diagnosing the early stages of the tumor. And here we suppose that these blood markers may be apparent even in the early stages of illness. Thank you.
Another question? So, I guess I would like to thank you once more, and probably some questions.